Hi, everyone. I am András Telcs from the Wiener Institute, and I will speak about something almost no way related to GPUs. Sorry for that. But later you should see that maybe there is slight connection, and that will be a puzzle for you. So this is a joint work with several colleagues from different institutes, among others from the Clinical Institute of Neuromedicine. The topic is very old. What was first, the chicken or egg? Or if you turn the question more scientifically, which causes the other, which influences the other, the chickens, the egg, or the egg, the chickens? Or if I turn it into a problem of physics, then let us consider two chaotic systems. We observe two time series out of the systems, and we would like to find out, without interference with the systems, without touching them, just observing them, if the two systems are autonomous, there is no link between them, or there is a link, so one influences or causes the other, or vice versa, or they are coupled in both sides, or, which is the most challenging problem, there is a third system which is driving, influencing, causing, both we observe, but we don't observe the third one. So the puzzle for you, during the lecture there will be a little spot where high performance computing, GPUs will come in. At the end you have the floor to find and spot that part. So let me start with a little bit of history. Wiener and Granger coined a principle later called Granger causality principle, which has two axioms. First is evident, the cause precedes the caused. The second that is coming from statistics. So imagine that we try to predict the next stage or time step of one system, and we do in a way that we consider all the past of that system and develop a statistical tool, something to predict it. Or we do the following: we observed both systems, we consider the past both systems, and based on that more rich information, we predict the future step of one. And it is quite evident that if the richer background provides us a better forecast, it means that the left out system causes the other one. Adding that history to the prediction improves our prediction. So that is the Wiener method applied to autoregressive processes, and medical and biologists and earth scientists were very, very happy with the method and used for many, many decades. So the method was worth for a Nobel Prize. But there was a question. If we are biologists and we study ants, can we come to a proper conclusion using the Wiener method, Wiener-Granger method? So let us imagine we have a test bed and we put one ant on a day on the test bed here, and we put some food somewhere else on the test bed, and the ant earlier or later will find the food and eat. Next day, we put two ants on the test bed, and we release one and the other, and we recognize that the second aunt follows the first one. So we observed two systems. We can record the speed and position of the two aunts. So we have two time series. And now comes the question whether the first one causes the second one or not. And of course, everyone knows very well that in case of aunt, the day before, the other aunt put some senses on the track, and the other aunt simply follow that, which is a perfect case of common cause. So they have no link to each other, but there was a cause the day before which forced them to move in that way. So we need something else to find out if there is a common cause behind our observations. And that needs a little bit of mathematics, but I won't go into the details. So basically, imagine that we have a system A, which is moved by a mapping F from one step to another step, from t to t plus 1, but we can't follow all the parameters of the system, only a function of it, xt. With a nice function, g doesn't matter. Okay, what can we do then? Let us compose a vector, so-called time delay embedded vector, out of our observation. We should choose m enough high. If we do so, then the Tarken's very famous theorem says that we shall recover the original state space of the system. If we have enough many data, this xt will cover the same manifold, at least from point of view of topology, as A runs. So we have a sheet somewhere where A runs, and we have another folded sheet where X runs. And the key point, they are topologically equivalent, and consequently, their dimension is the same. For physicists, if you like, I would say the degrees of freedom of the two objects are the same. So that's the fundamental fact we try to utilize. Okay, imagine, and let me give you the very simple example. We embed in 2 dimensions X the theory, the observation theory, that is the embedding dimension, and we embed it in 3 dimensions. And as a result, in 2 dimensions, in case of the logistic map, you can see here the iteration, we get a very nice one-dimensional something. But if we embed into 3 dimensions, the dimension is not increasing. Still, we have a banded but topologically equivalent one-dimensional object. Okay, so let's try a bit more complex situation. Again, we shall use this nice mapping. We embed xt in 3 dimensions and y as well, but we do some trick, and we make a joint embedding of the 2 observations. Doesn't matter if we take 2x or y, only one, or vice versa. Okay, so we embed y into 3D, and we receive a one-dimensional something. And here, if we incorporate x into the embedding, we get a richer something, a sheet, a kind of 2-dimensional object. How can it be? That means that x contributes with some extra information to the system we have here, which means that the information is in x independent of y. So in this way, we are able to detect independence. Now let us consider another example. We have axis here embedded into 3D, and we get a shape of 2 dimensions. If we incorporate in a joint y, we got another shape, still 2-dimensional. What does it mean? Y is not contributing with some essentially new information to the joint system, which means that it is already incorporated in X. Consequently, Y is causing X. Y is already used in the development of X. So that is the observation we are going to utilize to find out the causal link between systems, having only observation, no interaction with the systems. Okay, for that we need something, a little piece. If we have this cloud of the data set we have, the sample data set, we should measure the dimension of the cloud, the sheet, the line in the high-dimensional object. The dimension we have to estimate. And if we have that, one remark, this dimension, the intrinsic dimension of the manifold or sheet, theoretically equivalent with the information dimension of the random variable which covers that sheet as the mapping runs around the system evolves on that object. Okay, so what we do, we embed X, we embed Y, and we produce the joint embedding, and we calculate, estimate at least, the dimension of the 3 objects. And based on little information theoretic considerations, we can claim that the joint manifold has dimension strictly between the maximum of the individuals and between the sum of the individual dimensions. And we can go further with this full picture. If equality holds on the left-hand side with one of them, it indicates that we have a one-directional causality between the systems. This is just the opposite direction. If all the 3 are equal, then we have a circular causal relationship between the systems. Of course, as I mentioned earlier, we have an independent case. Then the dimension of the joint is simply the sum of the 2 separate dimensions. And finally, that was the goal of the whole story. If this joint animal has dimensions strictly between the 2 boundaries, that indicates that we have a common cause. Well, if we picture on different scales the previous examples, for instance, y drives x, here the dimensions are depicted, and we see that perfect match is found between the joint and x. So this is a synthetic example, of course. But let us turn back to our original problem, which already picked by 2 statisticians in 1988, and they wrote a paper about the problem in an American agriculture journal, taking more than 27 years of production of chicken and egg as time series, and try to figure out which causes the other. And they have used the very famous Granger method, and come to the conclusion that X came first. So we took the brevity and recalculated the case, and we found something else. The joint is, for different scales, strictly runs between the individuals and the sum of the individual dimensions, showing that neither egg nor chicken drive the other, but there is a common cause. I don't know which. Can be weather, can be market, but something. So, well, that's just a game, but there are more serious applications, at least we hope there will be some more serious application of the method. We are in collaboration with a medical institute where very serious epilepsy patients are cured. In particular, surgery is done to save their life. But it is a very difficult question which part of the brain should be removed to release them, to help them to be free of epileptic seizures and a big panel of medical experts come together to make a decision before the operation. So once we got a telephone call, can we send you the data? We are not sure what to do. So we got the electrophysiological measurement, a micro EEG, from this network, 64 channels, but they helped us to indicate that a few of the areas are suspicious as the core, as the focus of the epilepsy. They have the imagination that the epilepsy is affecting a big part of the brain, but one is triggering other areas, and that is and the result, the outcome is that the whole network starting to shake. So we got the question, we started to run our program, saying that we have no enough experience with the method, but let us try. And we found that in the resting situation, all the areas in the suspicious regions mutually drive each other, while during epileptic seizures, one area drives the other three. Here we have common cause effect, and in the other cases we have still mutual driving, which is typically suppressing the common cause signal. So this shows that at least our method is self-consistent. All the triangles are self-consistent in this picture. So we sent them the results, of course, warning them that this is just a vague indication. So the panel finally decided to remove the pinkish areas, saying that the area we are pinpointing is very deep in the brain and dangerous to remove. So they did the surgery. Thanks for God, the patient became quite healthy and free of seizure for a year. But after the year, the seizure reoccurred. Of course, nothing to do with our arguments, but at least we have an interpretation based on network analysis that they removed some very sensitive areas which were attacked by the focus many times and became very easily excited. They removed those. They lowered the excitement of the whole network. But after a while, the focus triggered again and again other areas and made the system again shaky and excited. So that is the story. Let me add one point. Let me search for one slide here. This is also a slide which relates a bit to the previous lecture. Of course, we can measure these dimensions, but those are only estimates. So to have a bit more accurate picture, we use a Bayesian machinery to come up with probabilities. So we can assign probabilities to the different possible causal relationships between the systems. And what you can see here is just, again, a test on the logistic system. If the ground truth is direct causality, well, we have a very high probability for that. And also for the circular, for the common, and for the independent case, which shows again that the method and the estimation of us working quite okay. Okay, let me finish. That we would be very, very thankful if you have a question about the causal relationship between systems and data, and you provide us. We are very happy to run our method, find out, can we say anything about the question. And now comes your turn. Where was the point where GPUs or high-performance computing comes into the picture? Thanks for your attention.
So, any questions?
Is there any relationship between these considerations and more general things like, say, mutual information and correlation, so more statistical description of different
Thanks for the question. Yeah, okay. It is almost common sense that causation is not correlation. Yes, the Granger causality method was later, which is a parametric method, later developed towards a non-parametric method called transfer entropy, and that is fully an information theoretic based method. And yes, in our method we also have some very simple information theoretic arguments. Either you can use the mutual information or conditional informations for the proof of the basic results. Is it the answer for your question? Okay.
Any other questions? Then let's thank András again.
Thank you.